Hi, everyone. I'm Todd Kennedy. I'm going to talk to you about multi-client syncing strategies. I'm the CTO of a company called Scripto. That photo was taken in May, so I'm also a beard grower, apparently. And I'd also like to say that I'm super excited because my only other coworker is speaking tomorrow, who's Mariko Okosaka, and you should go see her talk as well because it's phenomenal. What I'm here to talk to you about today, because we have a problem. What we do at Scripto is we make software for producing television shows. So it's the writers use us to write scripts, and then we automate some of the production details about how the show actually goes on air and gets filmed. So we want to be able to let multiple people edit the same document, but merge conflicts are really bad. I'm assuming a lot of people in here have used Git before, and I'm positive every single person in this room at one point, if you use Git, has managed to push without, or pull without pushing, and you get these really weird conflicts back that's like, you can't do this, your state's out of state. And you get all these massive conflicts because someone else has been working in Git, and you've been working in Git, and you haven't synced your changes correctly. And then Git will eventually say things like, you've got a three-way merge and a detached head, and you Google those things, and you actually get no helpful answers from them. So we want to be able to let non-technical people edit the same document at the same time. So luckily there are a bunch of solutions to solving this problem. There's a couple of very well-known algorithms. There's operational transform, which is what Google Docs currently uses. Google Wave really popularized it though. And Etherpad also uses it, which is a sort of Google Docs predecessor / clone. Google actually bought the company that made it, hired the staff, then open sourced the software, and that staff went on to make the new version of Google Docs. There's differential synchronization, which is what the original version of Google Docs used behind the scenes, as well as, if any of you use Linux, gedit uses it. There's a multi-user mode. Apparently, I haven't used gedit since like 97, probably 98. But apparently there's a multi-user section of it uses differential sync. And then there's also conflict-free replicated data types. Which, if you've used React is sort of based around this concept. SoundCloud uses it for their data stream. It's interesting because it's not a multi-user thing, it's sort of just pushing data out. But League of Legends actually uses it for their chat system, believe it or not. And they're one of the largest users of it, apparently. So differential synchronization is sort of like where it's an easier to sort of wrap your head around algorithm, so I'll cover it first. It was mostly penned by this guy named Neil Fraser at Google. And he uses character-based diffs to track changes between documents. And it's actually what Google Docs is really based on. So you've got a basic example in a non-network setup, and it's weird because when you look this up, the first example is always a non-network setup, and you're like, how are multiple people editing the same document? Never mind. In a non-network setup, there are two copies of the text at any time. There's the copy you're actively editing, and then a copy in your data store. And the trick is that it keeps making changes, then marking your current version as you change it into an old version, handing the diff off, and then moving the active copy back into the shadow again. So you sort of get this weird algorithm here where you diff your active copy against a shadow copy, you send a patch, you copy the active copy into the shadow copy, then you apply your patch to the data store copy. So it looks pretty simple at first. You're like, oh, I can really wrap my head around this thing. And then you look into how to edit multiple clients. Like how can I actually let multiple users do this? And you start looking at diagrams like this. Please note that they've got 5 copies of the document per user stored in the system at this point. 2 of them on the client, 3 of them on the server per user. So you actually end up using a lot of memory. And then the longer the document is, the diff algorithm gets really, really, really slow. So this isn't really the best way to do this sort of stuff unless you really like servers. The cool part though is that it's much simpler to get your head around. It allows for out-of-order application of changes because they're just diffs. You can apply a diff at any point in the transition, maybe get something back out of it sane. But you can also work with that as central server. You don't need anything actually coordinating changes. You can do that on the client. You can use like WebRTC or something to send the data across. Scaling is really complex though, and it's memory intensive. Diff match patch doesn't really work for structured data. If you've got multiple people working on like an HTML document or an XML document or a JSON document, it's really hard. We've all been in Git and it's tried to patch our JavaScript or try to patch our code and you get invalid code out of it. because Git doesn't understand, the patch algorithms don't understand the semantics of that. They don't understand the structure to it. And you can also track the user performing the edit in bands. You know, in Google Docs, when you have two people typing, you can see your friend where they're typing and see where you're typing. You need something entirely separate from this to track where the user is in the document. So then we also got conflict-free replicated data types. There's two types of them. There's commutative replicated data types, and there's convergent replicated data types. I'm going to kind of go through this because I'm going to really get into operational transform in a second. And then you've got a system called Woot based on those sort of methods. Woot is interesting because it's the only one I've seen out there that specifically references a different version of document syncing and says, hey, we're not like that, we're something entirely different. So it's kind of like a, hey, screw your operational transform. The cool part about it is it does not require a central server again. And all the papers say that it's less complex than OT, but having read the white papers, that's very debatable because the white papers for this thing include ridiculous amounts of math and formal proofs and algorithms, and the only implementation I found was really in Scala, and I was like, that's okay. The interesting part about it, though, is you can't delete data. Because of the way it works, the instant you delete data, it actually it gets marked as hidden. So as your documents grow and change, you actually start keeping in band a whole bunch of data you actually no longer need, but it's the only way to actually perform the synchronization between the documents at that point. Which brings us to operational transform. Operational transform originally developed in 1989, actually, as a method for syncing graphical displays. So they were actually getting users to share the desktop together, not just the document. So it's based around the concept of structured documents. It's not just text. You can edit XML, HTML, anything that has a structure to it. Xerox PARC had some hands in sort of getting the algorithm refined, and then Google in the mid-2000s came out with Google Wave and actually made a massive contribution to the algorithm by doing that. And the point of operational transform is that is the serialization broadcast of specific operations performed on a shared document of equal length with respect to the document cursor. The document cursor is a really important concept to grab here. It's not where you are actually typing, it's where in the document the edits are being made. Where you're typing versus where the edits are being made is a fine distinction, but you can be typing way ahead of where the edit's actually being made on other clients. Your clients can be massively out of sync with this, and it doesn't really matter. So there's some basic operations. You can insert characters, you can delete characters, and you can retain. This is like the most basic version of operational transform out there. So let's change an example. I just moved to Seattle, so there's a Seattle reference in here. Let's change I like Seattle, and let's uppercase the S and be proper with grammar. So the first thing you want to do is your operation is retain 7. So we count 7 characters into the text. Now the document cursor is at the 7th position. We delete the lowercase s, we insert an uppercase s, and then we retain the last 6 characters in it. So now we have a set of operations that can be applied to any document of this length to change the 8th character from a lowercase s to an uppercase s. So now that we've got them, how do we use them? So we have this thing called transform. Obviously, the transform method is the heart of the operational transform algorithm. And what this does is it really allows us to take these operations and apply them to a document in a way that's conflict-free and doesn't lock the document from editing. So the one caveat being, though, you have to apply these change sets to documents of the same length. So the reason we had to do that retain statement and that last retain statement is we actually know how long the document is before we can apply our changes to it. We can't apply changes to a document of a different length than that. You actually will fail, and you'll throw exceptions in a lot of these libraries at that point. And that's sort of what allows operational transform to do what it's doing, is it knows that it's applying to a sane shared document at that point. So we'll do a better example. We've got 2 users editing a document that have the characters T and A. User 1 inserts O, user 2 inserts P. So we got retain 2, insert O, retain 2, insert P. So now the document's diverged. We have 2 different edits of it. We have 2 different states, and we want to reconcile those. So we can apply both of those transforms, or both of those changes into the transform function, which give us 2 new document states back out. We've got A2 and B2. But this only works because they're of the same length, and they're also based on the same revision head. So they're both edited on the same document. And you can sort of see the divergence right there in that nice little ASCII art. So transform returns an A2 that looks like retain 3, insert character O. So now we can apply that to the document state, and we can achieve a singularity. So because we've retained 3, we get to the end, which is now tap, and we add O, and we end up with tapo. And you can see the sort of convergence happens. But I know you're thinking, tapo is not a word. But the awesome part is that it's a conflict-free resolution. There's no errors, it's up to the users using it to make sure that they're typing proper English, but this is gonna apply your transforms in a way that makes sure that you don't run into resolve issues or 3-way merges or heads or, weird states where you can't reconcile your document with the server. So the trick here is, though, this is a pretty simple system. So we're going into much more complex systems. And the trick is the server here is really, really, really essential. That's why the other 2 are interesting, because they don't require servers. You need a server and operational transform. So what happens here in a basic algorithm, or the basic sort of flow, is that the client emits a change set, the server sees it, the server accepts the edit. As the server is working on accepting that edit, in other words, saying that, yes, this is good and it's valid and I'm going to take it and I'm going to send it to the rest of the clients, your local client, you're still typing. So your local client is caching all of the changes you're making and not sending to the server until the server says this is good. And then I'll get into what compose means in a second. And then your client pushes back out all those change heads it's been keeping in memory after it receives the accept. The server at the same time, when it accepts, broadcasts to all the other clients saying, here's an accepted commit, please apply this to your changes before you send me any more changes. And that's sort of what allows the system to actually work. So it pushes the work for synchronization and data safety to all of the clients, which makes the client algorithm a little trickier than the server algorithm. But it means that anything arriving at the server can be immediately inspected and rejected if it doesn't actually match the shared revision head or the shared length. So when the server accepts the commit, though, it'll assign the unique identifier, and that's how we know what our shared revision head is. Our system uses just an increasing integer. It just adds 1, so our revisions count from 1 to 6,000 at some points. It extends the accept, and it broadcasts the change out. In reality, you're going to get way more diverged states here. So the transform allows us to do this. We can keep transforming sort of these intermediate steps together to come up with a composite change set that allows us to bridge between multiple document states. So when we got that other transform out, we can apply that to our B copy and get B2, which builds another leg. And then we can apply that and get C2, which allows us to reconverge our document. And I made a little animation here in Canvas that sort of shows how this works, where it keeps building all of the intermediate change sets between it, and as the document states diverge, you can keep converging down on your document state by building these sort of ladder sort of step change sets into that. And it seems a little laborious, and the problem with, this is where Google really comes into the picture here, is that transform is a really expensive operation to make. It's n log n, and you're doing this in the client. So with JavaScript, this can be really slow. Thankfully, Chrome makes this a little faster for us. But then Google comes in and makes up this thing called compose. And the cool part about compose is that it's O of n, so it's a really quick operation to perform. And it takes change sets and it collapses them together. So up here we have this massive long line of change sets. Compose can actually just put those all up into one change set again. So if you keep editing on your client and keep making changes to your client, it can go back to the last time you accepted a commit from the server, and it can collapse all of those change sets into a single change set. So rather than doing this crazy step walk across, we're back up at the top, where we're in a single diverged state from each other, and we can reconverge that state almost immediately with one transform. So we can take that compose train set, and we can just get, sort of AB2s where we're composing it together. We can throw that into the transform and get our new transform back out, which gives us back the legs, so we can get it done a lot faster. Thank you. That's it. I've got time for questions.
So I want to implement this in my code. I know there's Derby, Share.js. What can I go to hit the ground running with this idea?
The question was, I want to implement this in my code. What do I use for it? We're actually based on a fork of Etherpad Lite, which has a change set mechanism. Share.js is pretty cool. It's used on a couple of sites. I know JS Fiddle actually uses it behind the scenes to do that. There's a couple of them. If you Google into this long enough, you'll eventually see a bunch of ex-Google Wave engineers complaining about operational transform and how it's actually really complex. and how none of them, there's trade-offs when you're implementing across the board. So it's really depends on your system and what you're trying to do with it. Are you trying to edit structured data? If you're trying to edit structured data, there's certain versions that are better for you than if you're just doing text. Etherpad Lite is really text-based. Share.js is way more into structured documents. So it really depends on your requirements for that. Any other questions?
Yeah.
Yes.
You kind of actually just partially answered it. What sort of documents are you talking about? Like what sort of documents have you actually applied this technology to, like text or JSON or more structured?
So the question was, what sort of documents have you applied this technology to? Our system is just text. We've got some rich text markup in there, just some very simple bold tags. So again, HTML really, and we just for those operations we have more operations. They're called insert tag and insert end tag, which allows us to do that. Google Wave actually was XML documents, so they had a whole bunch of different transforms in there that allowed you to alter sort of parameters on elements, add elements, remove elements. So depending on the complexity of your document, you add more operations to it. And those operations sort of keep things in line, so you don't end up applying a diff on top of a partially formed HTML tag.
What about, just complex object graphs? Is that something that you're looking at?
For complex a complex object graph, you could do it with a complex object graph. It depends on the operations you've written. So if you have operations that handle inserting and removing elements from that object graph in a where you can sort of like, if your object graph has, if it's a straight line, it's a simple one, I've got 4 objects in, I'm going to insert a new object, and then we retain the last 4 objects there. Yes, and that's the Google Wave version was much nicer in that respect. And you can find versions of the Google Wave out there. None of them are canonical. I think Apache actually took over Wave. But that's a way more rigorous sort of inserting, removing, and editing of an XML document based in this system. So. Any other questions? Great. Oh, yes. No, so this is actually, the question was, is this your in-house implementation? We're diverged from Etherpad Lite, so we're originally a fork of Etherpad Lite. We're still the change set algorithm from Etherpad Lite, so the transform and the compose is from Etherpad, and the editor is from Etherpad, but that's sort of, we've extracted that out. Etherpad Lite's interesting, it's written by Java developers and it's JavaScript, so it tends to throw during asynchronous operations sometimes, so we've taken that out, because that's very hard to deal with. So, awesome. Thank you very much.